Here is a result that looks like a mistake. Two identical jobs, same cluster, same query, same 2 billion rows. One finishes in 40 seconds, the other takes 12 minutes. The only thing that changed was the file format the data was stored in. Not the code, not the cluster, not the query, the file format. To understand why, you need to understand what Spark actually has to do before it can process a single row. It has to read the data from storage, and how you have laid that data out on disk determines how much of it Spark has to read, which turns out to be the dominant cost for most jobs. Start with the format almost everybody reaches for first because it is familiar. CSV. A CSV file stores data row by row. Row 1 is written, then row 2, then row 3. Every field in a row sits together. To read any row, you read all of it. Now, our fraud job needs 4 things from the swipes data: timestamp, card ID, merchant ID, and amount. Our swipes table has roughly 200 columns: a transaction identifier, device type, entry mode, terminal ID, response code, dozens of derived fields added over the years. In CSV format, to get 4 columns, you read all 200, because all 200 are sitting in the same row, interlaced, and there's no way to skip to just the ones you want without reading past the others. Now, the alternative. Parquet is a columnar format. Instead of storing data row by row, it stores it column by column. All the timestamps together, then all the card IDs together, then all the merchant IDs together. To read 4 columns, you find those 4 columns and read only them. The other 196 columns are stored separately and are never touched. The same table stored as vertical columns with 4 columns highlighted and a file reader touching only those 4 columns, the rest untouched, labeled Read Only What You Need. On our 2 billion row table, 200 columns, and you need 4. In row format, you read 100% of the data. In columnar format, you read only the bytes for those 4 columns, roughly 2% depending on column widths. That ratio applied to 400 gigabytes is where most of the 12 minutes went. But column pruning is only the first advantage. The second is compression. Columnar storage compresses dramatically better than row storage. When similar values are packed together, compression algorithms can exploit that similarity. A column of timestamps is mostly small integers incrementing slowly. A column of merchant IDs for a single day of grocery shopping at one chain is likely the same value thousands of times in a row. Compress a column of repeated identical merchant IDs, compressing to almost nothing beside a row of mixed fields compressing poorly, labeled same data, dramatically different size. The third advantage is the one that makes Parquet genuinely different from just storing columns separately: row group skipping. Parquet divides its data into chunks called row groups, configurable in size and commonly around 128 megabytes by default. For every row group and every column, it stores the minimum and maximum value that appears in that column in that chunk. These statistics are stored in a footer at the end of the file, and Spark reads the footer before reading anything else. A Parquet file drawn as stacked row groups, each with a small statistics panel showing min and max values per column, with a footer label at the bottom. Now watch what happens when your query has a date filter. You want transactions from the last 30 days. Spark reads the footer, checks the timestamp column statistics for each row group, and any row group whose maximum timestamp is older than 30 days ago cannot contain any matching rows. Spark skips it entirely. The bytes in that row group are never read from storage. A file with 6 row groups, the footer being read first, 2 row groups being skipped with crossed out arrows, and only 4 being read, labeled skip before reading. On a year of historical data, a filter for the last 30 days keeps roughly a 12th of the data. Without row group skipping, Spark reads everything and filters in memory. With it, Spark skips the old row groups at the storage layer before any data crosses the network, before any executor touches a byte. This is predicate pushdown from episode 4, pushed all the way to disk. The same mechanism that moved your filter before your join now reaches down through the execution engine, through Spark's reader, into the file format itself and tells it which chunks to skip. Now, pause and think about what all three of these buy you together. Column pruning means you read only the bytes for the columns you actually need. Compression means each byte represents more rows. Row group skipping means you skip entire chunks before reading them. In combination, a query that would have required reading 400 gigabytes of CSV might read 3 gigabytes of Parquet. The cluster, the code, and the query are identical. The ratio of data read is not. One practical note about using Parquet effectively. Row groups work best when the data inside them is sorted on the columns you filter by most often. If your row groups contain random timestamps, the min and max for each group will span the entire date range, and no group can be skipped. If your data is sorted by date, each row group contains a narrow date range, and most groups can be skipped for any date filter. Two approaches here, and they are complementary rather than alternatives. Partitioning your data by date on write creates separate folders per date so Spark skips entire files for date filters without reading a footer. Sorting within each file by date makes row group statistics tight, so Spark skips row groups within the files it does open. Both together give the maximum benefit. Two row groups side by side. One labeled random order with a wide min-max range and no skipping possible. The other labeled sorted by date with a narrow range and most groups skippable. So, here is the big picture. Row formats store data field by field across a row. Columnar formats store column by column. Columnar formats let you read only the columns you need, compress similar values dramatically, and skip entire chunks using statistics before reading a byte. The combination of these three means that for most analytical queries, the file format is the single highest leveraged choice you can make, and it is made before Spark is ever involved. 12 minutes to 40 seconds. Same query, same cluster, same data. Just a different answer to one question. How is this stored on disk? A summary strip reading column pruning, read only what you need, then compression, similar values pack tight, then row group skipping, skip before reading. Next time, the other half of the layout question. Not how columns are arranged within a file, but how files are arranged within a folder, and why getting that wrong turns a fast job into one that reads everything, regardless of the file format.